So, are we live on YouTube? Or is going to dev null again?
Dev null.
Check. Works? It's working. Okay. So hi, and welcome to another workshop today. And let me go here. Get some slides as well. So basically, last week actually we had Mikk Mangus talking about more software topics, which I think is a great addition to these technical talks, because I would say one key aspect of this whole cloud native buzz is actually making your organization dynamic as well. That you sort of give up this ticket monkey stuff that you might have going on in your company. That in order to create DNS records, you have to issue a ticket, and somebody needs to get the ticket assigned and actually make the change to the production. So I think these kind of software topics greatly complement the technical talks. But today we're back to again a bit more hands-on stuff, and today I'm gonna try to condense quite a bit of content into this 1.5 hours. And talk about different ways data is stored when you use Kubernetes clusters. So actually in the original email I used persistent workloads, but then I realized that persistent workload doesn't actually make sense. We're talking about stateful workloads, meaning that the applications that are running, they need to carry some sort of state which you cannot just forget or drop. So yeah. Just to refresh again why we are doing this and what we are doing. We're doing workshops and talks on cloud native and security. The sign-up URL is there. If you just happen to randomly check out this video on YouTube or whatever, it's not too late to sign up and take a look at the content that we have already posted on YouTube. And throughout these months, we're going to do a bunch of workshops where you'll have some hands-on experience with Kubernetes clusters, and actually already set up a evaluation dashboard, which I'm going to show later as well, that I've started evaluating some of the stuff that I would like to see that you have done in the cluster. And once you have checked out all the checkboxes, then basically after March, we'll give those people who have done all of the workshops access to this cluster just to play around and have fun, do something for themselves, basically. And of course, the end goal of these workshops is to get more people interested in the hackerspace, because one aspect is having people here physically doing their whatever interests them, like, I don't know, restoring some older computers or whatever weird stuff that we have here. But the other aspect is actually having, let's call them like virtual or remote members who are maybe just interested in Kubernetes clusters, learning more about Kubernetes clusters, and providing them also some sort of membership options, which necessarily might not even involve like having the physical access to the rooms here. And the perk for you, everybody, would be that you can upskill yourself and become more competitive on the IT market, because I think. For many of you, the reason why you're here is that you have realized that if you're not picking up Kubernetes skills, you will be obsolete at some point. And this whole thing is supported by Startup Estonia, so that's the reason why we have these logos here. But yeah, the point of this workshop, there's like lots of different options when it comes to storage and persistence in Kubernetes. I'm going to try to like iterate over all of the options that make any kind of sense, and then hopefully give also some suggestions like what you could do depending on the circumstances, depending on what kind of cluster you're running. Are you running on AWS, or you're doing something on-prem, or you use a VMware cluster? So the great thing about Kubernetes is that it's vendor agnostic, and these talks are not necessarily only about AWS, but also VMware, or also might be even a bare metal Kubernetes cluster where there is no virtualization layer involved at all. So all of these are like valid Kubernetes clusters, and I'm going to try to cover them a bit more broadly than you would maybe have AWS present the topic to you. Yeah, and debugging skills, and I guess the biggest aspect here is like removing these mental blocks. That how do I do this? And then I'll just show you a couple of options which make sense, and then you could maybe put the puzzle pieces together in your head as well. And afterwards we'll have pizza. So somebody needs to order the pizza. So what are these stateful things that we have in Kubernetes? Like, this is I try to like look outside the box completely. Like, what are the things that that have some sort of state that we need to persist over time? Because basically, in the Kubernetes world, the standard is that you would assume that the workers get restarted, they can get completely wiped, they can get replaced, because basically that's how a worker update or upgrade in a Kubernetes cluster works. In case of AWS, when you hit the upgrade button, it basically deletes all of the existing workers from the cluster and creates new ones. So it is assumed that you don't have any kind of live migrations or anything like that you would have in a classical VM world, that you live migrate VMs. That doesn't exist in Kubernetes. Instead, the workloads, the pods, they get destroyed in the old workers. New workers are created with the new software versions. Let's say you would have, I don't know, you would do maybe like Ubuntu upgrade from 20.4 to 22.4. And all of the workloads, they get deleted on the old machines and they get recreated on the new ones. This is the standard way how pods are handled in a Kubernetes cluster. And of course, this this isn't what you need for a stateful applications like databases. So we need to figure out how do we handle these kind of applications in a Kubernetes cluster, because it like intuitively does the opposite thing what you would expect. And I've just put on this slide like all of the things that you should consider which have some sort of state which you need to persist. I think last time we showed these configuration maps. Configuration maps is where we put some index.html file to serve it with an Nginx. In most cases, you would put the actual application configuration files into those config maps, and then they get mounted to a pod. These configuration maps would be stored in the underlying etcd cluster of the Kubernetes masters. So these are actually stored in the Kubernetes masters. There's the etcd cluster there which stores them. And the secrets are also stored there. And this is just one layer of all of the persistence aspects that we're looking at. The other aspect is Docker images themselves. One of the things that I guess you will realize is that you need to have a place to host Docker images. Even if you're purely focusing on running container applications, practically you cannot avoid like not having a Docker registry where you build and push images. Building and pushing images, we'll have a whole other session about that. I think Erkki Aas will present that. And so in this session, I wouldn't focus on the Docker images, but I'm just saying that Docker images, you need to store them somewhere. If you're on AWS, you would use this AWS ECR. If you do it on-prem, then VMware maintains this awesome project called Harbor, which is a self-hosted Docker registry with a nice web UI. So you need some sort of Docker registry where you can push the images. And actually, the hidden aspect with the Docker images is that the workers that will run your applications, they need to cache the images from the Docker registry into the worker. So there has to be actually some disk space where they can put them. And when you create these Kubernetes workers, that's what you would size the root file system for. So I think AWS by default puts like 20 gigs there. But I think 20 gigs is not enough. I would go for 50 or maybe even 100, because if you run all sorts of different applications, their Docker images do get cached in the machine that runs the applications. And depending on what kind of applications you run, let's say if you have a mix of Java, Node.js, Python applications, you will have like different root file systems. Each one will be something like 1 gigabyte, like Node.js base image is like 1 gigabyte. And as you have different versions of them, it will actually use up significant space in the worker. And yeah, these are like things which are Kubernetes specific. Now we come back to more of a traditional things. So you will always have some sort of dumb application which wants to write to a file system. You practically cannot avoid it. So I think, yeah, I actually put it here. It's I wanted to add here more bullet points, but then I would actually got sidetracked by talking about different things. But for the scope of storage, a good cloud application doesn't write to a file system. In fact, it should not even assume that it can write to any file at all. So in a well-secured Kubernetes cluster, you will have the containers running with read-only permissions. It cannot write to a file system at all. And this is like what I would call an ideal cloud application. That it doesn't assume that it can write there, and all of the data is persisted somewhere else. So in practice, this means that it uses MySQL, it uses Redis, it uses Memcache, and so forth. Yeah, I put here also that do not assume there is only one pod running. That also has an effect on the file systems because classical block devices, you can only mount it to like one pod. But there are some file systems which can be mounted into multiple pods at the same time. And if you don't know what you're doing, you can seriously screw up your data, basically. But yeah, generally speaking, do not assume that there is one pod running, even if you have replicas 1, because when you do an update, you will have actually the second one, the new one spawned simultaneously while the old one is running, and then the old one is being torn down after the new one gets up and running. So yes, file system, you will need to have some sort of way to do file systems. And actually, let's jump here. Again, more examples. Somebody mentioned Jenkins last time. And Jenkins is like a good example for an application that needs a classical file system. Because the way Jenkins stores data, it has this massive directory which is full of XML files. And there's like gigabytes of XML files. So it's when I looked into it, I was a bit shocked that who the hell does databases with like XML files. But yes, Jenkins does that. And to run Jenkins in a Kubernetes cluster, you would need to provide it with like a classical file system where it can write its stuff and, you know, figure out the rest, basically. Another example maybe is Grafana. Grafana, with its default settings, writes the dashboard configurations into an SQLite file, and this SQLite file needs to be written somewhere on the disk. Of course, if you would now look into Grafana deployment options, what they would recommend there is that, you know, please use a MySQL database for the data, and then you can actually run multiple pods of Grafana, and then they would be writing to a shared MySQL database. But yes, generally speaking, the implementation, there's so many implementations for classical file system in Kubernetes. If you're on AWS, then of course you go to the EBS volumes. You can mount EBS volumes to a pod, and it integrates with the rest of the AWS infra. So, you know, nothing new there. If you've already dealt with AWS infra, you just use the same EBS volumes inside the Kubernetes cluster. Now, when you do an on-prem cluster, or not on-prem, I meant self-hosted cluster, then of course you do not get any of the conveniences of AWS EBS because it's their proprietary technology, right? And in order to do a block storage, like classical block storage or classical file system for Kubernetes cluster on a self-hosted machines, you essentially have Longhorn, which is developed by Rancher. This is one popular option. And basically what it does, it runs the data-bearing nodes, it runs them inside pods, which write the data to the local disk, and then it makes it accessible to the other pods inside the cluster using eSCSI protocol. And it also does replication, so basically your application, while it's writing to the volume, behind the scenes it gets actually replicated to multiple disks, multiple physical disks. I think EBS actually does the same thing in AWS, but you just don't see what's happening inside there, because EBS is still I think it's a highly available block storage system, is that what you would call it. And the EBS volumes, I think they are on a block level replicated inside AWS infra as well. There's one caveat with EBS volumes. EBS volumes are bound to one availability zone in AWS. So I will have actually Rainer talk more about the availability zones and the whole topology, including networking topology, especially when it comes to AWS. But generally speaking, when you run stuff on AWS, you first choose the region. That would be like a larger geographical area. And within that larger geographical area, you get to choose availability zones. Like for instance, in Frankfurt, there are 3 availability zones. And you get to choose in which availability zone you run the application. The EBS volumes are bound to one availability zone, so you cannot cross-mount them between different availability zones. This has to do with latency, because the replicated block devices inherently need very low latency network, which basically implies that they are physically very close to each other. So that would be in a one data center, for example. But the different availability zones could be, like, for instance, different data centers or a bit further apart from each other. So yes, when you are designing the network topology of your AWS EKS cluster, then this is something that you might need to consider, that you cannot automatically move an EBS volume from one availability zone to the other. In a self-hosted setting, besides Longhorn, there is now also OpenEBS project. So OpenEBS, I think they just copied the name from AWS. Mayastore is very similar to Longhorn. I haven't tried it, but there's like basically a lot of stuff going on when it comes to replicated block storages in a Kubernetes cluster for self-hosting clusters. And interestingly enough, Ceph project, which was designed to build highly available block storage devices, so on self-hosted infrastructure. Ceph also has gotten this kind of a new breathing with Kubernetes, and there's this Rook Ceph project, which basically packages the whole Ceph infra as a Kubernetes. I think you would call it a Kubernetes operator. So it does something similar what Longhorn does. It runs the Ceph software inside the Kubernetes cluster and makes the disks that are attached to the machines available to the other machines. But generally speaking, I would say like these replicated block storage systems, which are running inside Kubernetes, like Ceph and like Longhorn, I would say both of them, they are rather new things, and they're lacking certain level of maturity, let's say. On the other hand, if you already have VMware cluster in your company, there's probably, I think if it's a bank, it's probably running VMware, right? Or if it's a government organization, there's something VMware related there. So if you already have VMware somewhere in your infra, then VMware has packaged Kubernetes. They call it the Tanzu project, and in that cluster, you get to use this vSphere CSI driver, which basically makes those VMFS volumes accessible inside the Kubernetes cluster. So again, very similar to what AWS did with EBS volumes. So the volumes that you would otherwise use on VMs, you can now use them inside pods. And of course, you always have local volumes, but the local volumes will have the drawback of being lost when you remove the workers or upgrade them or something like that. Yeah, as I said, note that the Kubernetes workers are considered ephemeral. Ephemeral means exactly that they have a limited lifetime and they are expected to go away at some point in the future. So, lots of options. Depends on the whatever use case that you're trying to solve. If you're on AWS, just stick with EBS, then you get well-supported infra that has been tested everywhere and should work always. And when you set up an EKS cluster in AWS, then like enabling this EBS CSI driver is just like a tick box somewhere in the UI that just please enable this driver in the Kubernetes cluster. So the databases are coming up in a moment. I just had to jam this Redis slide somewhere. So I suppose everybody has heard Redis, has used Redis in some setting or had to set it up or whatever. So Redis essentially was designed to make these highly available applications so you could update them, that you wouldn't have, like for example, in case of some PHP applications, you would have session cookies stored inside the PHP process, which means that when you shut down the pod or update it, all of these cookies get deleted, and basically the users get logged out from your awesome web service that you're serving, right? And Redis kind of solves that issue, that the session cookies, for example, are stored in a Redis instance, and then the application writes them into the Redis cluster and reads them from the Redis cluster. And then you can actually easily update the applications because none of that data is inside the application, it's stored in Redis. But Redis was never really designed for data persistence, I would say. So I think it was like, in hindsight, later added that, oh, some people have put some persistent data in the Redis. We should be able to somehow save it. And the way Redis persistence works is that it basically dumps the memory contents to a disk, and you can configure the interval. But basically, the point is that between the moment of last save and the current moment, all of that data would be lost if you would pull the plug on the machine that runs the Redis. So Redis is not exactly what you would call a durable data persistence system or database. And for this reason, I would highly recommend to not put any kind of data that needs to persist inside the Redis. Inside Redis. So Redis is perfectly good for these web sessions, cookies, anything that can get lost. You just need to keep them readily available with a low latency, and you need to be able to share it between your workloads where you have multiple pods running the same application. And this is where it fits nicely, but I would say don't use Redis for persistent data. And one good example is message queues on Redis. So for example, the Next.js web development framework, it's some hipster stuff. Hipsters like to use it nowadays, I heard. And Next.js bundles a bull message queue system in it. It's a Node.js, it's a message queue system for Node.js that builds on top of Redis primitives. And Next.js includes this message queue system, which means that people, when they are looking for, how do we do message queues, they look, oh, everyone else is using Kafka, but Kafka is so complex. And then they already see, oh, there are functions for using this pool message queues inside the framework, and then they immediately start using this. But the problem is that the message queues, I think, it's not acceptable to have a data loss for a message queue. That you restart the process and some stuff that is in the message queue gets lost. That could translate, for example, into, I don't know what would be a good example. Image being
money transfer started.
Yeah.
Lost the message.
Maybe a lamer example would be a person uploads a cat picture to the website. A task is put into the queue that we need to render differently resized images of this image, but then this job never gets done because the Redis contents get lost, and then you have a bunch of broken images on your website where the preview resized images are missing because they got lost from the message queue. So I wouldn't say that that's acceptable. So for message queues, message queues would be a whole other topic as well. For message queues, use something that is that properly persists the data in a durable fashion. Durable means basically that if the database has acknowledged that yes, this is written, then it's actually written to the disk, not that maybe it's written to the disk. And the other aspect is that keep your Redis instances small. So I've had the honor of having to maintain something like a 20 gigabyte Redis instance. It's very painful. There's like, let me give you a couple examples. When the Redis starts up, first of all, it starts up so slowly. It takes a couple minutes to actually load all of that data from the disk and get it into the memory. If you have multiple replicas, rebuilding replica takes time quite a bit. And the other aspect is that if you also use simultaneously the data persistence, it means that when you're hammering the Redis instance with a lot of writes, this memory usage grows significantly. It can basically double because of the way that it's implemented in Redis. But anyway, just keep your Redis instance small. Do not put any persistent data there. Web session cookies is a good example, but do not build like message queues on top of Redis. And now we get to the databases. So with databases, I put here at least like 3 examples, what are possible. So once you're at this point, I'm going to assume that you picked your favorite CSI, the volume implementation among all of the 10 options, and then I'm going to try to narrow down here what you can do next. So this is one of the scenarios we're going to do in the lab as well. You're just going to start a pod, MySQL server pod. Everybody's seen MySQL, right? Some of you might have had to administer it as well. So this is the lamest scenario where you are the database administrator as well, because you have to take care of backups and snapshots and whatever, which is not provided anywhere out of the box here. The benefit of this is that it's easy to move around data as opposed to some of the managed services. So I think AWS, some people have told me basically that AWS, it's easy to get data into AWS hosted managed services, but it's very hard to get them out of them. So you can move your Redis instance into a managed AWS Redis instance, but getting the data out from there, it's nearly impossible. So that's why I put here, it's easy to move around data that you can export it, you can do MySQL dump, move it elsewhere, and you can get data into it by having a dump and then importing it into this MySQL server. In this particular scenario, now you're relying on the block storage system replication. So if you have just EBS volume there, you're dependent on its SLA and availability. And by the way, I've had at least on one occasion a situation where EBS volume was lost. So AWS specifies the SLA for an EBS volume that we will guarantee its availability to a certain percentage. I think it was like 3 nines. I think it was 99.999. That we guarantee that the exists with that probability, but there is always the 0.001, and the 0.001 means that if you happen to be one of those unlucky people, then AWS just tells you, sorry, it's gone. And this has happened. I mean, just that you would be aware that you're having a contract with the service provider, and if shit hits the fan, then they will say that they have provided the service up to this SLA, but there is still a chance that you can lose the EBS volume. So point of the story here is that if you're relying on just single EBS volume, then you should have frequent backups and mitigate these risks in some other ways. And the other aspect is that the underlying volume might become a bottleneck. So EBS volumes have the throughput around 3,000 EOPS, depending on which kind of volume type you're using. But basically, it's in the magnitude of thousands of writes per second, which basically means that if you have a web application that is serving tens, thousands of writes, let's say 10,000 comments are being written by users, then if it sits on one single MySQL server that is on EBS volume, then that doesn't cut it. And you need to figure out some other way how to serve it. Another aspect here is that if you reboot the worker where the MySQL server runs, you will have an outage, of course, because there's only one MySQL instance serving this. And when you reboot the machine where this pod was scheduled, then you will have at least once outage for the moment when the pod is either started on another machine or during the time that the worker restarts. And yeah, as I said, availability depends on the underlying volume. But this is, at the same time, this is the easiest scenario, and we can easily do it in this lab. You just have a manifest that says set up MySQL server. This is the password for the root user. And then you can have some application that interacts with that database. Now let's go level up. In the manifest, actually, it says replicas 1. So some of you think, I will just put replicas 2, and then everything starts magically working. But that's not the case, because MySQL doesn't, just vanilla MySQL doesn't know anything about replication. It just starts one MySQL server, and that's it. And to actually run a replicated MySQL database inside the Kubernetes cluster, you would probably use something like something that's called an operator. I've actually listed here a bunch of different tools that I've used in this cluster. So I've got an operator for MongoDB, operator for Postgres, and also one for Minio. Minio is basically like a self-hosted S3 equivalent. And you're not actually anymore managing just the single pods or deployments or whatever. You have a high-level interface to the operator, which you just tell them that I need a 3 replica MySQL cluster, and then the operator takes care of figuring out where to place them, and it sets up a bunch of other things as well. Yeah, and this is called the instantiation through the custom resources. I'm going to show the custom resources later as well. So basically, like all of the manifests that we looked at last time, these are like official Kubernetes built-in resources, but custom resources enable you to allow you to define additional stuff using a similar manifest format, basically. Basically, let's call them in the layman's term, it's like plugins for a Kubernetes cluster to extend the functionality of the Kubernetes cluster. So in this particular setup, the MySQL service would be highly available. You can basically, okay, let's go through the topology as well, but basically you can reboot and restart every component in this topology. So here you have your application. There's the MySQL service definition as well. It actually has 2 ports exposed. It doesn't use the default, what is the default port of MySQL is something like 3306. It doesn't use that port anymore. These are the MySQL proxy ports or whatever they're called. And this is now being served by these MySQL router pods. And you have 2 of them running, so you can do updates again, because then when you do an update, you start up the new version, you tear down the old one, but continuously there is at least one pod which is available to serve your application. So you do not cause any application-facing errors by restarting the MySQL router deployment, which consists of 2 pods. And the MySQL router is the one which keeps track of which one is the primary MySQL server, and primary MySQL server is the one that accepts the writes. All of the other MySQL servers are replicas, meaning that they do not accept any writes. They can maybe only serve reads to load balance the reads. And the replicas are just replicating data from the primary. So all of the writes marked in the red, they have to hit the MySQL primary. Reads can hit the replicas, but write operations are not permitted to go into replicas. I think your replica, if you talk to replica and want to do an insert, you would just get some sort of error that I will not allow you to insert anything here because I'm not the primary. And each one of those servers would be writing to its local storage. This is just one possible option. But the benefit of this topology is that, as I said, EBS volume had a throughput of about thousands of operations per second. NVMe drives nowadays go to something like 2 million, 3 million. I think we already went beyond like 10 million threshold, yes. So NVMe drives, if you can talk directly to an NVMe drive, from a performance perspective, that's probably the best option. And yeah, so I hope that this is more or less understandable what's going on here. But you probably don't care any of the database internals. You just want to develop your application, right? So this is what you would need to do to run the database yourself in a highly available fashion, which in an on-prem scenario, in a self-hosted scenario is, well, the only way to go, because you have chosen the very masochistic path of running infra yourself. So somebody needs to run the database, and this is how it's done. It's complex. You need to figure out everything here. You need to set up monitoring correctly, etc. And but at the same time, even if you're totally running a hipster startup on an AWS, there might be cases where you would want to use this as well. One of the reasons is better support for upstream versions. So as you know, AWS provides a hosted Mongo service as well. Hosted Mongo service is stuck on this Mongo version 3 point something, which is the moment when they had different license for the Mongo database. And AWS basically grabbed the code base and made a managed Mongo service based on that code base. Mongo then after this changed the license, said, screw you, basically, I'm not going to allow you to do this anymore. And Mongo 4 point whatever and later ones have actually a different license, which basically prevents AWS from providing a managed service based on this, based on that code base. And in that case, this is one of your options. If you want to run Mongo 6, for example, in a Kubernetes cluster, then the easiest way to do this at the moment, I would say, is to use the MongoDB community Kubernetes operator, have it installed in your cluster, have it manage those highly available Mongo databases. And in this case, you would have something similar. Okay, Mongo doesn't have routers specifically. You would just have 3 Mongo replicas running in different availability zones. And yes, you would see the pods and you can interact with them. But that's like the only way you can actually run Mongo 6 in an AWS-based Kubernetes cluster. So there are scenarios where it makes sense also on AWS. And I guess if you would have some sort of application that needs like really high throughput databases, then it might be the case that you can just grab, actually, I just checked this morning, you can grab these very high performance, not even high performance, just bare metal workers or EC2 instances, and have them added into your Kubernetes cluster, which is in AWS. So it might be the case that you can just build your own high performance Mongo cluster by having 3 bare metal workers inside the AWS EKS cluster and run the Mongo nodes on top of those. And then you can actually use the NVMe drives as well, because some of the AWS bare metal instances, they have NVMe drives. Like you can get something like 2 by 1,900 gigs NVMe drives. So in that case, might make sense. I'm just giving you options and explaining why one thing, why you would want to consider some scenarios. And now the hipster startup scenario. You don't give a crap about databases. You just want to build your hipster Node.js application. This is what probably most people want to do as you're building whatever web application. So in this case, the database is completely managed by the provider. AWS has the RDS service. They provide MySQL there. There is Postgres, there is Redis, there is, I think, Memcache, and then they have their own flavors of all of these. Like they have 2 Redis offerings. I wasn't even sure why. I think they have built like a Redis compatible thing from scratch internally, and then they offer both like vanilla Redis and then their homemade version of Redis. So yeah, in that case, high availability is covered, because that is the whole point of having a managed database. You just push the responsibility to someone else that I don't want to deal with this. I will pay for you that you would deal with this. Importing data likely is easy. Of course, they want to get more users, they want to get more money, so of course they make it easy. But as I said, I think exporting Redis data from AWS hosted service was kind of a pain in the ass. And as I said, versions offered by the vendor might not be what you need. So if your application depends on, one of the reasons why you would want to use Mongo 6, for example, is that Mongo 6 supports these fancy change streams. You can listen on the database for changes. That's not even implemented in Mongo 3, what is provided by AWS. So yeah. And the biggest disappointment for me actually is that in order to use these services from Kubernetes cluster, it's kind of lapsekingades. What is that in English?
Preliminary.
Preliminary. It's kind of in progress thing, and in practice, everyone still uses Terraform to provision these resources. I suppose Terraform has some sort of tooling to put the secrets into the Kubernetes cluster, right? So that's what you want to need, at least for your application. You need to have the database host names, port numbers, usernames, and passwords to end up in the Kubernetes cluster, so your application can easily read these things and then connect to the database to actually run something. And the main problem with Terraform is that this is like a whole different world. It has nothing to do with Kubernetes manifests. It's like a manifest system of its own. It's developed by HashiCorp, which is another company. And if you would want to have something that is, completely contained in the Kubernetes manifests, then the closest option is this, for AWS, for example, is this AWS controllers for K8s. So they have wrapped the RDS APIs, and basically you can have like a couple lines of manifest to get an MySQL or a Postgres or Redis instance from AWS RDS, and then to get the secrets back to your Kubernetes cluster. So yeah, what future holds? I hope that there will be more of this automation inside the Kubernetes cluster. So maybe we could actually one day drop Terraform, that we don't need Terraform. And for example, there is this container object storage interface standard, which is being worked on at the moment. So there's the website, there's some working groups there, they're like designing these APIs and specifications. And the point is that this quasi standard, for example, will bring a bucket resource definition into the Kubernetes cluster. So you have an application that needs an S3 bucket. You just say, I need a bucket of, 5 gigs, and then it will figure out where to get it. But something like this for relational databases, like a universal standardized way of ordering relational databases or even not relational databases, that doesn't exist at the moment at all. And that was like my holy grail. That I think that eventually it will get there, but it will probably take a couple of years. And until then, what you can do? So of course you can continue using Terraform. But at least from many startups and companies, I've heard that they have built their own internal tooling to order these resources and automate the ordering of them. And what I would like to see in these resource definitions is that you hide the implementation away. Developers should not know like in which availability zones is the database running. Like it's none of their business really. And and similarly, the developers shouldn't need to specify, how big volumes are needed to run a MySQL database. They should have this sort of infinite MySQL endpoint where they can connect to and just write stuff. And yeah, some of the stuff that I didn't. It could go probably on for an hour or two just to explain the other stuff. What about backups? You need to figure out how to make backups. From database services, you also need point-in-time restore functionality, which means that, for example, the Postgres operator that I use here, what it does, it actually streams the write log to an S3 bucket. So basically, you have a continuous stream of all of the writes to the database, and you can changes, yes, to the database, and you can restore an arbitrary moment from the past. So that is known as point-in-time restore functionality. That you have essentially a slider, and then you can just go back in time and create a new copy of the database with the contents of that time, basically. So something to consider. Which like, do you need this in your application? Or how much do you need it? or are backups enough? Like, is once a day backups enough? But point-in-time restore is like one of the, let's call it like fancy enterprise features that you would want to have in a database setup. And sharding, yes. So sharding, this could probably be another long talk, but basically something to keep in mind when you're designing your database schemas and your applications. Do not grow one database too large. So a Mongo instance of something like 200 gigabytes is very hard to manage because of the same reasons what I mentioned on Redis. It takes a lot of time to rebuild the replica if you, I don't know, add a replica or just for whatever reason it loses a connectivity to the primary, then you also need to rebuild the replica. And if your replica size is like 200 gigabytes, it actually takes tens of hours to resync the contents from the primary to a replica. And I would say at this point that, keep your MySQL, Mongo, or whatever databases below 10 gigs, because those are, in those cases, you can easily rebuild the replicas. The replica rebuild will be something like 1 hour. Okay, depends on many aspects, of course, the CPU power and whatever. But if you grow them too large, you're going to have a bad time. And so you're asking like, well, if I have more data, what do I do? So from microservice architecture point of view, you're supposed to actually break down the database as well. So the way I see it nowadays is that a database is a part of a microservice, and the databases should be also separated into different instances as the microservices are separated. So let's say having a 200 gigabyte Mongo and then bunch of microservices that connect to the same Mongo, that is not really doesn't follow correctly the microservice architecture. And I would say if you correctly split up the database into different Mongo MySQL instances, most of those instances will be rather small. And then, yes, you will probably have some sort of data sets, like, I don't know, let's say credit card transactions. That would be, sounds like a very big data set, right? So for those few data sets, you would do sharding. And sharding basically means that you would break down the database into smaller shards. Each shard would be something like 10 gigs. But they would, in case of Mongo, you would have this sharding proxy in front of it, which routes the request to the right shard. The shard just allows you to, what is it now, horizontally partition or vertically horizontally partition one database table, let's say. So yes, sharding would be applicable, but just don't do it on one big Mongo. Just do it for the datasets that actually grow so large that you need to enable sharding for those. So, any questions so far? Yes?
First one, what's the reason for AWS export data? Why it's so complicated?
Why is exporting data from AWS complicated? Because they want to keep you as the customer. They don't want you to go anywhere else.
Maybe some technical reasons.
No, I would say it's only money.
Okay. And the second one is if big enterprise should go with plain Kubernetes or just with OpenShift, which is having Kubernetes underneath. Why do many companies go with OpenShift scenario?
It's the same.
Can I repeat the question?
Yeah. So the question was, why would enterprise would go with OpenShift? So OpenShift is a Red Hat provided, let's call it Kubernetes distribution with some bunch of bells and whistles, right? So again, it goes back to this. Where was it? You have offloaded some responsibilities was the, crap, I closed it. You have offloaded some responsibilities is the point. So let's say, I think OpenShift, they ship you a bunch of operators to actually run this infra, right? including probably something to do something to run MySQL databases. So let's say if they have a bug and it deletes all the MySQL instances, it deletes all your data. At least in case of OpenShift, there is somebody that you can sue. So there is somebody who could help you restore the situation, fix the bugs, etc. So it goes back to this, classical purchasing support and offloading responsibility scenario. But yeah, that's something for the business guys to figure out. What kind of issues are we trying to solve with this money that we're paying, and is it worth the cost? So there's no yes/no answers here. So you have to because if you're running, what would be a good example? Okay, let me give you a good example. I guess if you're a bank, then you have lots of money involved anyway, so you want to be covered in many ways. But if you're a university that simply needs to simplify running applications for students, you don't need OpenShift there. You can just run it yourself. If you accidentally delete all the databases, it doesn't matter. Because it was for a educational use case anyway, so it's not catastrophic if you accidentally delete all of the MySQL instances in a cluster which you use to teach students how to use MySQL databases. So I think it boils down to this basically. Any more questions? That was a good one. This OpenShift, yes, I should have put it in one of the slides. I just don't know enough about OpenShift. No questions? You're just sleepy.
I sleep with my eyes open.
So just to for the intro for the lab. So I've added here a bunch of examples that you can run on the cluster. So this lab 9 MySQL standalone is the very lame option of let's go through the manifesto, then you know what we're talking about. So it just runs the MySQL image, runs the MySQL the Docker container. It mounts a directory which is stored on a Longhorn volume. So very simple setup. In this case, we are not using deployment anymore. Last time, I think the kind that we used was deployment. So let's say stateful set and deployment are two different ways to run pods, and multiple pods actually. The deployment kind is mostly used in cases where it is okay to start up a new pod before you tear down the old one, which works nicely for stateless applications. Stateful set specifically is designed for applications where you cannot run the new one before you tear down the old one, because you cannot start a new MySQL process which is writing to the disk where the old one is still running. That will just mess up all of your data if you could actually trick them to start up at the same time. Because MySQL, of course, has mechanisms in place which will stop the new one from starting, even if you manage to give the access to the files. And for this use case, Kubernetes has the stateful set kind, and that's what it does. It will stop the old pod before it starts up the new one. So if you, for example, upgrade the version from 8.0.32 to 33, it will stop the old pod and then start the new one to make sure that only one MySQL process has access to the underlying files. But otherwise, it's very similar to deployment, yes. We have also here replicas 1, and I put specifically comment here that if you just increase it to 2, that doesn't make anything highly available. This would just start a new MySQL process with a new volume that is running next to it. So they would be like independently running without knowing anything about each other. And What else do we have here? We have the service definition, which makes this port 3306 available in the cluster. And just to play around a little bit, I have a PHP myadmin deployment here, which has all of the variables configured. So you just need to figure out what is the password of the MySQL root user and use it to log in to the MySQL database. Of course, change the username here. I put my name here, but put yours. And then there's the ingress rule to expose the PHP myadmin to the outside world, so you could actually access it from the web browser. This job is here, but this doesn't actually work. Let me delete this. I thought I was being clever, but that particular example doesn't work. Okay, push the updates. It's gone now. And let's see the other ones. I have a lab 12 for Redis. So this particular one, let's use the syntax highlighted one. So this is the kind of futuristic version of provisioning databases that I mentioned. So this is something that I wrote myself. It hides away all of the complexity of running a cluster of 3 replicas. You just basically say that I want to have a Redis cluster with 512 megabytes of usable space, and it does the rest. You'll see the pods will appear next to your application, and you can interact with the pods. I also added here an example application, the Redis commander, to talk to the Redis cluster, so you can do something like increment 1 and see that it actually increments and it gets recorded in Redis. And from here, you should be able to also see where the connection data is coming from. So this Redis cluster operator creates a secret where it puts the password, and that's the secret you should be able to see in the kubelens UI as well. And then there's an ingress definition to make the Redis commander accessible over the web. Again, change the username here. So, like you could just modify the MySQL standalone example to run Redis instance as well, but then you wouldn't have the high availability. And actually, the tooling that I've created also has support for MySQL and Postgres, but let's try to not make it too complicated at the moment. And yeah, I think I didn't even mention the S3 buckets. So next to classical databases and NoSQL databases, you also want to have S3 buckets. This is again something that I wrote, but this is the kind of user experience that I would want to see eventually happening in the Kubernetes world. That you don't need to write Terraform code, or you don't have to even specify availability zones or anything like this. So let's get started somewhere. Let's see that you can actually start the MySQL server. Start with the lab 9, and then let's check out the others as well. And let me know when you get stuck somewhere. Is anyone tracking the YouTube comments?
I was watching and there's one person that says like reading from Tartu or something.
Shout out from Tartu.
Tartu, must be Eno.
Links don't work.
Live stream'is lingid ei tööta.
Links are not clickable.
Kas sul see Kubernetes setup on kuskil alles? Seda repos ei olnud.
Dashboardi peal on kõik ju.
Oli.
Mingi saab ligi ka kuidagi.
Sul invite'i võtsid vastu?
Enda alt küll jah. Sest et kui ma tagasi korraks
mis see mingi niimoodi jah? Ei ole saanud. Nii nüüd on olemas. Sul peaks olema kutse kuskil mailboxis, mille kaudu ligi saad. You also don't have an invite? What's your username?
This one.
In my SQL log, it needs to change in 2 places.
Sorry?
In my SQL log, it needs to change value in 2 places.
In 2 places, okay. So if you're doing this for the first time, open up the dashboard. If you don't have a dashboard, hit the button to create a dashboard. And if you haven't configured anything, you just copy paste this to your shell. This works on Mac and Linux out of the box. On Windows, you need to understand what's going on and then replicate it on Windows. And to apply the manifest, use this context flag to specify which kubectl config it uses. So it shouldn't, like, none of this should interfere with whatever you have maybe set up from your job. And you just do this. Okay, it's already, I think I have already set it up. And then you should be able to access phpMyAdmin -Lauri Võsandi. And then you need to figure out how to get the secret, which was set up for this scenario. The lab 09 actually. It actually has here the command that generates the password. So it's nothing special here. Basically, it uses kubectl to create the secret, but it generates it from random bytes. You can write there manually something yourself as well. That would work as well. But in any case, you should be able to figure out where you can find it in kubelens, for example. Go to secrets and MySQL. Which one was it? MySQL standalone secrets. This one. And then you need to hit this show button to decode the base 64 as well. Then you can copy paste it from here and you can access it over the phpMyAdmin. So let's
Sorry,
yeah.
Siin peal siis oma sandbox nimi, jah?
Jah.
See
on see altrof bnpzt. Ja siia peaks selle konteksti ka juurde panema tegelikult.
okei .
seal cluster access seal näiteks . kujuta jälle , vaata see kontekst , miinus kontekst , seega panen juurde . ja ilma if-ita .
ilma if-ita ,
jah ,
okei .
if there's anything , jah ,
If I have secret created
so do you have the kubelens installed as well? From kubelens it's I think it's easiest to find them, and then once you have gotten a bit more comfortable with you know, knowing what even exists out there, then you can try to figure out how to write the command to get it yourself. So let's see, kubectl. Okay, I need to add the context here as well. kubectl get secret MySQL standalone secrets. Yes, okay, that doesn't give you much useful. It just says that secret exists, and then you can do something like output it in YAML. But outputting it in YAML gives the string in base 64 for whatever reason. And I think then you can do something like JSON path. But for JSON path, you need to say, let's see. There is probably that does it. With a Go template. Oh Lord. It's so ugly. That's so ugly. Yes, that's the root password basically. But I mean, I wouldn't remember this anyway. So you just go to Google and search kubectl get secret decode base 64, and then it gives the string. You cannot see the secret, but have you generated the secret? There's this in the Git repo. Go back to the Git repo.
Yeah, I should create secret before. I just deployed.
There is this almost you just need to add the context to specify in which namespace it goes to. But this is like a command that generates a random string for the password.
But if the cluster is running and I will generate secret, it will take effect.
I think that it's not running at the moment because the secret doesn't exist. Hmm? No, but the MySQL server. Look into kubelens.
No, looks like no.
Why there are no pods? But stateful sets? And from the right namespace? By the way, okay. There is one gotcha with these kube access controls. Here in settings, put it into the namespaces listing which namespaces you're working on. Otherwise, it doesn't automatically discover some of the resources. Let me show. So this one, settings, in namespaces, I have specifically added the namespace that I have access rights to, because you don't have like a full cluster access to read everything, and if you don't specify the namespaces that you have access into, then it hides some of the stuff.
Yeah, I see. No
Like, there's no pods, there's no secrets, but click here in settings, namespace, and paste it here, the namespace, the context name, or not context name, namespace name. Dem sergo something dash blah blah blah. And then hit this enter, yeah. And then go close it with escape. And then I think just to refresh on the or disconnect even maybe. I click here.
Why?
No. Disconnect and then connect again, so it actually like reloads everything.
This still works okay.
Huh?
Is this still working okay? I mean the lens stuff. Yeah, I don't break frequencies.
Did you type the namespace correctly?
Lauri,
No küsi. Yeah.
question, philosophical one. Based on your experience, what is a safe approach to take by an enterprise, growing enterprise when trying to embrace Kubernetes?
That's a very
Some scenarios, but
that's a very broad question.
Maybe I need to pull this stuff.
But Sergey, look, the MySQL pod is not running because the secret is missing. You haven't created it. Yeah. That was a very broad question.
yeah, I'm just thinking that, for example, if you take some semi-helped AWS approach, then you basically don't have the full picture if you want to implement a full-blown alternative yourself, right? You have basically you have partial information about the system. If you
Yes.
want to, for example, get rid of AWS and then you suddenly discover that you don't have the full picture on the situation.
Yeah, but that's the whole business idea of AWS. They take care of all the complex stuff. Okay, this doesn't work on Mac. Nice. Okay. Teeme midagi. Let's see.
ma proovisin
Paneme siia mingi lihtsalt, ma ei tea, sala-kala. Already exists? Okay.
jaa, seda juba
Okay. Mis ta sinna pani? See on olemas ju?
jaa, seda olemas, aga
Jah.
seda on.
Nii, kas on midagi katki ka praegu? Ei ole?
ja lihtsalt ma ei saa minna praegu see dashboard.
Nii, mis ei saa? See on PHP MyAdmin, mitte MyPHP. So anyone needs help with something?
I have to change here.
Let's go back? No, go back to the shell. Okay, the problem actually here is... Yeah. It's more than namespace. This is actually this context. Context doesn't exist. Have you configured it? It's this. This is your kube config file. Okay, let's see what's the problem.
Oh, maybe it's different one.
Wait. No, go back. Yeah. Yep, it's different one. Yeah. So, how are you doing?
Better link installations. Better link installations.
You're installing stuff. Okay.
know why in Mac sometimes the commands are taking so long time, but maybe it's just going through some process.
No, I actually think that there's I think there's some bots hammering this Cube API endpoint, and that's why it's a bit slow sometimes. Somebody's DDoSing it. So you got the secret set up. Yep, that looks good. And then try to get the manifests applied as well. No, kuidas sul on? Seal dashboardis peaks olema need... Ei tööta? Nii, mis viga on? Nii... Aga näita seda, näita manifesti, mis sa kirjutasid. Nii, mis seal all lõpus on? Ingressi juures need seal teise all. Nii, jah, ja. Jah, see näeb õige välja, aga kas...
Kui ma vaadasin lensis,
nii.
siis on point 2 Nginx ja veel kus on ingress. See on ingress.
Sul on üks sandbox ainult või?
Jah.
Okei. Ja vaatame siit. Nii, see on ainult see siin. Aga kas seda manifesti, mis sa sinna applysid, kas see läks läbi ka sul või? Et kuidas selle peale panid? Nii. Siin on see fail ka, -f ja... Nii, nüüd võiks tööle minna.
Okei. Ma mõtlesin, mis ma keelisin teeb.
Näe, nüüd tekkis. So, I have a question. You on the config, no, that like that one. Okay, and you're missing the secrets. Did you configure this namespace here? Hit on the that one. Open up the settings and namespaces, and just type this Jousima that thing only, yes, and then enter. And then close it, and then disconnect and reconnect again, and then it should show the secrets. Yeah, you can disconnect from there, and then connect again. Yeah. Otherwise, you could read all of the secrets in the cluster, and that would be kind of bad.
It would make
life easier, right?
So here it would.
Mm-hmm. That's actually base 64 encoded, so you hit this one now. That's the actual password. And root. Tada!
Kus sa selle koodi saad? Ma olen kõik ära unustanud.
Mis mõttes koodi?
Millega sisse logida.
See on see samas, nii hall ongi.
Selle ma lõin läbi, aga see ei tööta eriti vist.
Mis mõttes ei tööta?
Ma sain ta siia sisse.
Sa nüüd mõtled üle, pane lihtsalt tuimalt copy-paste'i see shell'i.
Ja ei, ma tegin seda.
Nii?
Ta genereeris selle faili alla.
Ja.
Aga kui ma proovin seda teha, siis ta annab mulle sihukest stambaid.
Sul on see mingi OpenID logini see asi on puudu. Vaata sinna dashboardi lehele uuesti. See kube logini, vaata, see on sul nagu puudu.
Selle peab installima, või?
Jah, see on see, mis seda OpenID autenti võimaldab teha kubectl-il.
Okei. Huvitav, eelmine kord on...
Ja mõtlegi, viimane kord sul töötas ju. Mis tegid siis vahepeal?
Ma ei ole mingit reinstalli ega asja teinud. midagi vahepeal teinud.
sa loksutasid seda suurt jõudu sellega, et sa hakkasid sellega tegelema. Selle kohta on jumala näide tänasest päevast. Vaja mingile Vintsile, mõtlesin, et kuidas ma saan Vintsile vaatama.
Okei, so, sul töötab? Sa saad ka tööle?
Mul on nii palju on ees, et see tuleb siit, aga
Okei.
kaugemale ei ole jõudnud väga.
Okay, see on juba väga. Yep. And nice, you got it in Japanese. But the password is in the. You can either look at it in Kubelens or have you got Kubelens installed as well? No. And then you can also do this. So you can also do kubectl get secrets like this. Let me do it like this. Yeah. But this thing will be base64 encoded. Encubed. But yeah, I think most of you got it running actually. Let me just actually quickly demo a couple more things. I mean, because that was the whole point, like getting MySQL running, and then you can see that, wow, it's actually in Kubernetes, right? Just to get the feeling that you have actually managed to get it running at least once in your life. So when you try to do it next time, you at least know that it is possible. But beyond the MySQL, the other labs that I have listed here, let's see. I'll just show it on the screen and then we'll call it a day. Lab 12. So in this particular setup, let me grab the command from the dashboard again. This one. So in this case, I'm using this my custom resource definition for Redis cluster, and there's basically a bunch of voodoo happening behind the scenes. Let me try to like explain in a moment what is happening behind the scenes. And this is generally speaking, this is how most of the operators work. There's a pod somewhere in the cluster that runs. It observes all of the definitions that are in the cluster, and it's just like a tiny Python program. It connects to the Kube API, it watches all of these Redis cluster definitions. If there is a new one that gets added, like looks like Sergei added the Redis cluster, so it sees that this definition was created and it does something. And this particular Python program simply creates a service definition for the Redis, it creates a stateful set for the Redis pods, sets up 3 of them, sets up the configuration in the way that the configuration of the Redis instances sets up the replication, which one should be replica of another one. It actually does a bunch of things in the background which would be very annoying to do if you need to do it repeatedly. And that's the whole point of the operator. It's called operator pattern, that you hide away, you tuck away this implementation details, and you just have a very abstract request that please, I want to have a Redis cluster. And all of this actually, the stuff that I have written is publicly on the web. It's this operator bundle because it does a bunch of things. And just to illustrate the point, like what it does for the Redis. Lots of if and else's. But for example, these manifest fragments you can already see here. It creates a service definition, but these are programmatically generated, and these would be very annoying to maintain if you have them manually written in a manifest file, basically. So it basically, let's call it in the lamest term, operator is like a template engine for manifests. But the end result for this particular scenario is that I have 3 Redis pods. They are scheduled on different machines. If I go pull the plug on one of the servers, then everything should keep running as expected. And these 3 pods get exposed via service, which actually does load balancing between all of the pods. Load balancing or failover, which way, depends how you configure it basically. So if one of the pods dies, then a service level IP address should still continue responding and keep serving up the connections. The Redis commander is just, I guess this is just to demo an application. I actually started this cluster, I think it's been running now 3 hours and 9 minutes. So I already did something there. I just did something like increment ASD. So that's one use case for Redis. You would use it for counting. But Redis Commander, I think, is a nice tool to have a web access to a Redis instance if you want to debug something. And of course, the other ways to interact with the Redis cluster is that you would do a port forward from the cluster to your local machine, and then you can use Redis CLI from your local machine to connect to the Redis server that is running inside the cluster. So yeah, this is what I was actually like 2 years ago when I started with Kubernetes. This is the kind of level that I was expecting, but that's not really the case still in reality. And that's why we end up writing these things ourselves. And the other piece, the other lab that I have listed here, this one, no, this title is this is misleading. I haven't changed this. That's my bad. Lab 14. So this does something similar for S3 buckets. kubectl, let's do kubectl apply for this one as well. It's already, I think, already set it up. In this case, there is no pods are created in my sandbox. For this particular setup, I have actually a separate namespace where the cluster is running, and then there is only one Minio cluster that is there, one shared Minio cluster. And the operator simply creates a new bucket inside that cluster, and it brings back the secret into my own sandbox. And if we look into the secret, you know, there are the familiar things, AWS access keys. Well, we have only one region, so it's US East 1. There's an endpoint where you can connect through. There's a secret access key. And actually, if I copy paste this, I have actually exposed the Minio web UI over the internet as well. So you can grab the credentials and log in here. So that's the password, and that's the username. Username actually takes the form of namespace dot the definition name. And if I log in, this is my bucket, just one bucket where I uploaded. I uploaded something here. That's neat. So point being here is that if you want to do like a totally cloud native infra, like forget Terraform, you basically need to hire somebody who is able to write operators. But what I can say based on my experience is that it's not that hard. Most of the stuff is just, you know, create the user account, create a database, grant access to this user, and give me the secrets back and put them into the namespace where the applications can read them.
Until something unexpected happens.
Yeah, of course. So, but
Start listening to this tutorial.
but generally speaking, like if you think that, you know, this is outrageous, that, you know, we are writing something that managers are very delicate infrastructure, then, you know, just to illustrate the point, So this external DNS component that I showed last time. Only AWS and Google Cloud are marked stable. All of the others are alpha, beta, alpha, beta. So generally speaking, if you do like Kubernetes outside AWS and GCP, then you're pretty much on your own anyway. I think this point holds for the other stuff as well. Like, you know, if you're in AWS, use the RDS, you know, you will pay, but you will get something at least for that money. But yeah, this was just in a way to show the journey that I've been through as well. If you want to self-host all of this, it is possible, but you know, the caveats are there and there's lots of them. So yeah, I think this concludes the workshop. I hope you learned something new. There wasn't, I mean, of course, from a manifest point of view, main applicable thing here is that you know that there's a stateful set kind, which is used for these kind of applications. For some demo setups, yes, you can set up your own Redis or Mongo like that using the stateful set. But in reality, you probably want someone else to run these instances just to save your own time. And if you're on AWS, you basically, in practice, you need to go back to Terraform to provision these resources, which in the scope of this lab, I just can't, I don't have, I'm not going to write a Terraform provider that you can use to play around. So that's why I showed these manifests. That would be the way you could provision these resources in the cluster that I have provided. Because generally speaking, you will be using vendor provided tooling to provision these resources anyway. On GCP, you would use something else, but something that Google has, you know, built. This reminds me, a couple months ago, I was accidentally happened to talk to Hannu Krosing. Hannu Krosing is an Estonian guy. He wrote the book on Postgres. And we ended up having a beer. And he's now working at Google in Zurich. He's actually building like the managed Postgres service for Google, I think. So, and yeah, that's what he does now. So that's what happens once you write a book on Postgres. You get hired by Google. But the funny bit was that many years ago, when I was young, I happened to, it's completely unrelated to any of what we've talked about today. I happened to debug this, there was this, what is called Katlamaja. What? Chimney, no chimney. It's like a heating facility. Let's call it heating facility. It used wood chips to burn and then heat up the water. And then that was like, I don't know, 20 years ago. And then it was this crane that put in the wood chips that was running on Red Hat 4. And it had a UI written in Python 1.5. I had never used Python 1.5. Like that was like, I don't know, 20 years ago, or like I wasn't born when it was when Python was at the 1 point something. And then I just remembered that the username of the account that was logged in on that machine was Hannu. I just randomly asked him like, "Hey, did you write that thing?" And he said yes. So it was his high school project to write a UI for a crane that was putting wood chips into the furnace in a whatever heating facility. Just a very random coincidence that, you know. And yeah, so now he works at Google.
And probably still logged into his Hannu.
Yes. So yeah. In this cluster, I showed you the way you can use Redis, the way you can get buckets. In a similar fashion, you can get MySQL instances and Postgres as well. So let me show you quickly. I'll just open up this one. So the usable things that are in this cluster include MySQL database, include Redis, and include I think I also have here now post, I think it's typed like this, Postgres database. Mongo I haven't implemented yet because Mongo is a bit trickier. But all of this should be usable in this cluster. It will just save some time if you want to quickly get something up and running. And this class basically, class is let's call it like a implementation selector. Like I've got a bunch of different implementations in the background. If you would use, for example, Redis, if you use Redis dedicated, then you get 3 pods in your own namespace. Like it creates it where you have defined it. If you use shared, it puts them into this separate Redis clusters namespace. So you don't see any of the Redis pods. Because if you have the Redis pods in your own namespace, you can just, you know, in a crisis, what you would do. Oh, we need to restart everything. You select all pods and kill them. So you don't want to kill the Redis pods. And that's why I added the shared class, in which case the pods are in a different namespace, so you do not accidentally delete them. And the dedicated you can also use, I think, for MySQL and Bucket, but don't use dedicated in most cases because it will create separate persistent volumes, separate pods, separate everything. So the shared ones are like, you know, classic kolkhoz, that you have one instance and all of the databases get created in that one, which for this particular setup is fine because you're learning and trying out. But if everyone starts creating like MySQL clusters, then we just run out of disk space on the machines. And this actually kind of reminds me the IT college setup that we had. We had this enos.itcollege.ee. He had exactly the same thing. There was one central PHP myadmin instance, one MySQL cluster, and the students get to make the MySQL databases inside that cluster. So the class shared basically implements exactly the same thing. But I guess that's it for today. And let's see, next week, are you on next week? 50-50. So I guess we'll continue with the minimum effort. And I'll send an email next week what will be the talk next week. So if it's Rainer, then it's going to be about networking, mostly AWS networking, how to design the network topology. If it is not Rainer, then it's probably Erki who will talk about how to do scaffold, how to use a scaffold to develop applications in a Kubernetes cluster. And that will also, that presentation will also cover the harbor that we use here. So this thing, the Docker registry. Oh, it's already 900 megabytes used. But that's it for today. I hope you learned something new. And pizza is there, right? Okay, excellent. Then I guess bye-bye YouTube, and we'll see you next week.